Okay, hello. We're gonna have a short review. Today is all we're doing this week. I thought I am gonna do just reviewing in the sense of here's the things that will appear on the second project. So you can see on the agenda there's no homework this week, there's no lab this week, there's no discussion. So I'll just take this opportunity to read through the requirements of the second project and make note of the tools and techniques that will be needed um, to complete the second project. And so that'll go pretty quick, I think. Anyway, hopefully you're having a good week, and we'll get to it and we'll get you out of here pretty efficiently today, barring any questions. All right, so just oops, wrong direction. Okay, so where we're at in the semester, the second individual project is due December 11th, which is less than 3 weeks away. Well, you can tell that here. Um, and then we have one more. So the week of finals, I don't do a final exam. Your last project will be behind you, and we'll just have a normal content week that week where I will um, and attempt to show you how floating point values work on modern processors. I find it very interesting. So the last week, you'll have a homework lab discussion as always. Some of you may find yourself in a position where you can kind of carefree experience the content. That'll be up to you. But anyway, that's what's happening. So let's just go straight to. Anyway, I'll show you real quick. If you click on the module for this week, you will find not the usual stuff, but instead, I wanted to make that disappear so you don't have to look at it. Oh man. Okay, that's better. So week 14, there's just this one page. So if you go there, it'll just tell you no assignments this week. I am encouraging you to have a look at the second project. If not, start it. If not, knock it out. Most, if not all of it, you can do. I don't maybe I'll get a little bit of code sample today. I'm not sure. But anyway, let's go read through the second project, and I will make note of what is required. So there's a fair amount of narrative here. The second project, not surprisingly, is going to have you exercise the skills and knowledge that we have been working to acquire since the first project was completed. So we'll have dynamic arrays in there. We will have, which means dynamic memory management, so mem.alloc or mem.zalloc and mem.free. We will have summing values in an array that will require the addition instruction from x86. Averaging the values will require summing the values followed by some division, so we'll get to review division. The minimum value in the array, we did that in the lab last week, and it should be relatively easy to turn that into the maximum value. That's just comparisons and memory accesses, and that's it. So this used to be a much bigger project, but I found that people were kind of just mailing it in at the end, which just caused extra work for me for no gain for most students. So I backed it off to the kind of the bare essentials for a final project. But if you've been doing the labs all along, then I already know whether or not you're sort of experiencing the content that we need to experience. So the requirements, documentation. This doesn't happen. In fact, it hasn't happened in either of my computer architecture courses in several weeks now, but I've been grading some PNA 1 assignments, and a lot of them are leaving those 25 points on the table. So please do, before you call it done here in a few weeks, review the actual rubric with the points associated and check these off to make sure that you've done them. I don't worry about the quality of the source code itself, but you do want your program output to be neat. You have several tools that you can use in this class to do that. Clearing the screen is relatively easy, and that's a good one to use. Let's see. Dynamic memory management. using random values, which I did an example of that in lecture, not that, maybe last week or the week before. A few algorithms that require you to use most of the math instructions except for subtract, but add is the same, so that doesn't really matter. So one thing I have backed off on here, I think, yeah, so if you choose to deal with like the sum of values causing overflow, it's not required, but you can. You're encouraged to do it, but it's not required. So anyway, these are the technical requirements and the points. If you're doing all of those things, then you're good to go on the second project. Anything extra you want to do is certainly invited because the experience is always good. Yeah, with a loop. So what does mine look like? Tell me how big. Manually enter all the values or use random values. So if you manually enter the values, you're just going to loop through the whole thing and get values for every position from your user. And then you'll produce some calculations, and that's the end of the program. What this program used to be is kind of a miniaturized spreadsheet with switching the display mode between binary, hexadecimal, and decimal. And anyway, I just found that most people were not troubling themselves because they realized they had enough points anyway. So I just whittled it down to what I want to be absolutely sure I've given you a chance to demonstrate. So the second project, if you look at the code for it, especially if you look at the code, if you were to travel back in time and look at the code earlier in the semester, will look complicated. But for you guys at this stage of the semester, I think it'll be relatively straightforward project. Okay, yeah, so there's those things. I guess I'll switch over and I'll just kind of spin up a little starter just to kind of talk about how I would go about setting this up. And while I'm at it, I'm going to show you a feature of the HLA language that we haven't used yet. And it's a high-level programming feature, but I'll go ahead and show it to you. You may or may not choose to use it. Let's see. I need a I'll just call it P2. All right. So if it were me, of course, I'd have documentation at the top. I'm just putting that there so that you don't forget, because that's 25 free points that there's no reason to leave on the table. Two. And I think we've gotten used to looking at a lot of code in HLA at this point, so hopefully nothing about looking at the HLA code itself is bothering anybody anymore. And you should be encouraged by that here in just the span of a few months, you have basically learned another programming language. And it's got some things that are quite a bit different than something like Go or C++, because you are mixing in x86 assembly instructions. The syntax has got some kind of like old Pascal stuff in it. So even that, I think, is a good part of the experience, is just to realize that you can pick up a new programming language, and in just a few months you can write productive software in it. All right, so you're going to need this, of course, as always. And then for my money, you're going to need two static variables. And this, as a point of review, the purpose of the static variables is to give them the scope or lifetime of the entire run of the program. So these are globals, and we frown upon globals in high-level programming. You shouldn't use them unless someone forces you to. But at this kind of much lower level of programming, if we are going to maintain data from the start of the program running all the way to the end of the program, then we need to have a lifetime for our data that represents the entire span of the program. And in HLA, the way you do that is with static variables. So you should, in theory, only need two of them. You should need a place to store the address of your dynamically allocated array. and you're going to need a place to store the size of the array. D words are 32-bit kind of raw data, and it is a good way to represent the address of things in 32-bit assembly. So we are doing 32-bit assembly in this class, which means that all of the addresses of things are 32 bits. Hopefully everyone's gotten that straight in their head. The size of the thing and the address aren't related. So an 8-bit value, and like an int 8 variable, has a 32-bit address. It just does. It's weird that the address is bigger than the data itself, but in 32-bit assembly, all of the addresses are 32 bits, no matter what they are the address of. So this array variable will be used to, that's how I would do it anyway, to store the address, which would be the base address of a dynamically allocated array. And then you can also use that to free the memory associated with that array when you are done with it. The reason why we want a static variable for that is that we want to, it would just be bad programming practice, in my opinion, to leave something as important as the base address of your dynamically allocated array up to the volatility of the registers. Another way to say that is you shouldn't store anything that you need long-term in a register, because the registers are volatile. They get overwritten a lot. So something like the base address of your dynamically allocated array, the only way to guarantee, or at least the wise way to guarantee, that you're going to have that address available when you need to access the memory or when you need to free the memory is to store it in a static variable. Also the size, because you need to have easy access and convenient access to how many elements you have allocated space for in your array. You need it for all of the array-based algorithms. You need to know the base address, and you need to know how many elements are in it. And then you will write code to do the scaling part, which you have to do manually in assembly language. Okay, the reason why that's an UNS 32 is because this size, its main job in life is to facilitate memory accesses. And because memory is 32 bits, variables that we will associate with accessing memory should be in 32 bits. It makes life a lot easier if we just, everything associated with memory work is going to be 32 bits. Okay, so that's our static data. We shouldn't need any other. I can't think of any other static data that you need, but you're not restricted from creating more static variables if you want them, but you don't need them. Okay, so what else do we need? We need procedures. So if it were me, I would probably just kind of plan on having a procedure to represent every major operation in the program. Create array. I don't think that any parameters are needed for create array, but I'm going to show you an HLA syntax feature that we've never used before, but you might find that it pleases your sense of order to do this. In HLA, what we have been doing all along is we just fire up the procedure, and then what we make sure of is that the procedures are defined in order so that any call to a procedure will never come before the definition of the procedure itself. So in other words, this is something that I couldn't do. So I cannot do this in HLA. So I have this procedure start program that calls create array before create array has actually been defined. You can't do that in HLA. HLA will not let you call create array until it's seen a definition for it. So what we've been doing all semester is we've just been saying, well, I'll just be careful to make sure that I have actually defined create array before I ever call it. But there's another syntax that you can use in HLA that is more like C++, for those of you who have experienced C++ at this point. We can get around the whole order of definition thing by doing what's called forward declares. So I can, wait, let me put these back. Okay, so right now I have a legal code. I have start program calling create array before create array is defined, but I can get around this with forward declarations. So I can, for example, I can forward declare, that should be a semicolon. I can forward declare the create array procedure so that now I'm allowed to call it before it exists. So I'm going to set my project 2 up to do this. It pleases my sense of order a little bit because I can just go to the forward declarations and I can kind of see all of the function interfaces, meaning what are their names, what are their return types, and what are their parameters. Anyway, so this is the new HLA syntax feature that we've never used before. And you can choose to use it or not to use it, but I'm going to use it today just so that you've seen it kind of in practice. And in fact, I'm only going to do forward declares, although I am going to make sure it compiles before I leave it in your hand. So let me see what happens if I forward declare that right now. Okay, duplicate symbol, line 8. So interesting. What this means, probably, is that HLA has this array as a reserved word somewhere, maybe in the libraries. So the various tricks to fix that. Some people, you'll see it in their code, they'll put little m's like my array to avoid the duplication of terms. So because the compiler wouldn't accept the word my array, I'm going to change it to m array. And then I'm going to go ahead and change size to m size just so there's a familiar pattern there, which I just consider to be good practice. That way, when I'm looking around my own code, because of this little array problem, I'm just going to make the other variable kind of match the pattern. Okay, so yeah, I'm getting a grouse about a forward declare without a corresponding definition, so that's fine. Just making sure I compile. Okay. But anyway, so I'm going to set up a forward declare for all of the major operations in the program. So we have a part where we create the array, and we have a part where we delete the array. I think the delete array, I'm going to go ahead and receive the address here. Okay, so I'm forward declaring it as well. There's a little bit of a funny highlighting thing going on. Okay, so some of you might wonder why I've been doing this, and it's another just sort of best practice, at least in my opinion. Why would I not have a parameter to create array, and I would have a parameter to delete array? Well, create array, there's no additional information I can supply that function that is needed. I expect, and I think, let me see where the @returns comes. Let me see if it's there or if it's in the other place. This one I forget some. Oh, darn it. Yeah, let me, I'll put that in a second. Okay, so the reason why a create array has no parameters is because there's no information in the program anywhere that I need to supply it with. So I don't. Delete array, so why do I have an address parameter when I could just access the address global variable? And in my opinion, it's because I don't want to get into bad programming habits. simply because I have to use this static global variable in HLA. Good programming habits are when you can use the parameters and the returns of a function to move data between parts of the program, you should do so. So even though I don't need to pass this address because I could just access it directly, it's better software design and it keeps me in better habits if I don't make a procedure that is dependent on a global variable. So at least as much as I can avoid it. So in my procedures, I'm going to avoid any reference to the global variables because I would be a bad programmer, in my opinion, if I did that. So yes, I could just get rid of the parameter and access the global variable directly, but bad habit, bad practice, I'm not going to do it. So one nice thing about this forward declaring is that I can alphabetize my procedures, which seems like a kind of a silly, I guess they match. It seems silly that I would care about alphabetizing my procedures. But I think it makes for a nice orderly piece of software to do that. It also means that if I'm reading through the code later and I want to hunt down a procedure, I know that I can kind of go through them alphabetically to find the procedure implementation I'm looking for. So I'm going to alphabetize them in the forward declares. I'm going to alphabetize them when I define them. And because I'm doing forward declares, that means that any sort of necessary ordering I'm freed from. And now I can do my nice alphabetizing and not worry about what order the procedures appear in. So create array, delete array. I have a series of procedures related to min. I'm just going to call it min. I think that's a reasonable thing oh wait, before I do that, let's talk about return values. So I want the procedures to kind of be completely independent as much as possible. I realize that the main part of my program is going to have to work with global variables, but if I can avoid that in my procedures, I will thank myself for the good practice. So create array, I'm going to call that from the main part of the program, and then I'm going to expect to get the address back in a register. So I need to set, and I need to remember if this is required in both places or not. So anyway, create array is going to return the address of the allocated memory in EAX, and then in the main body of the program, I will invoke it, and then I will move that address into my marray variable for long-term storage. So I'm going to try to contain as much of the messiness with the global variables to the main block of the program and try to keep my procedures as clean as possible. Let me see if that is how you do that. Okay. Just need to make sure it compiles. I don't think, by the way, so notice I didn't repeat the @returns here, and I don't think that you do. Let's see if it complains about it. Yeah, it does. So if you start forward declaring, the documentation of return values, those are going to go with your forward declares. This @returns declaration doesn't actually make the procedure return something, but it does allow you to access a compiler trick. So what does this @returns allow you to do? Well, the way I imagine using this is I would say create array and then move EAX into my marray. Static variable. But because I have this HLA syntax feature, returns EAX, I can actually use the call to create array in places where EAX might go. So I can actually, because of this returns EAX, I can call create array inside of the move, which will be executed, the compiler will literally execute the function and then put EAX right in this spot. And then we move EAX containing the address value. We copy that to marray. So I hope that made sense. This at returns, all it does is give you the ability to drop the function call into a place where you would have placed DAX otherwise. So I can take this 2-line create array sequence and I can replace it with a 1-line create array sequence because of that at returns flag. So up to you, but I figure give you something new for the trouble of watching me do this review. Okay, so now we can think about, and I'm not going to do all of these, but just, in fact, probably just one of them. So the minimum value, what do I need? So I'm going to need the address of the array I'm working with, and I'm going to need the size of the array I'm working with. I expect this to return a 16-bit value because we're doing int 16s in this project. So the minimum value will be an int 16. And then I'm forward declaring that too. I guess I can kind of bunch the forward declares up. So it is extra code and extra work, but it allows me to make prettier code, in my opinion. And then I'm going to get and then I can also alphabetize not just the forward declares, but the function definitions themselves. Take the part that I need. Do a to-do, make sure that it compiles. And then I would alphabetize them just because that pleases my sense of order. And I suspect that I'm not unusual among us programmers in that. Okay, so that's the forward declare syntax for HLA. You do forward declares in C++ if you have done C++. You have the same limitation. You have to declare or define a function in C++ before you can actually call it somewhere. Same rule in HLA. This is the HLA syntax for doing those forward declares, which means now I can call them in any order that I want. So I just left those as to-dos. Anyway, this is how I would set up for this, is I would make a procedure for every one of the major activities in the project. So we'll get a max, we'll get a sum, we'll get an average. You could use the sum and average together with each other if you have the sum return a value, as opposed to just print it. So that's something to think about. What else would I say about this? Let me switch over and see what else there is to say. Random value, yeah, so I would have, so let's see, average, min, or average, max, min, sum would be them in alphabetical order. We have the delete the array. We're going to need a way to print it, obviously. There it is being printed in this screen cap. So I'll go ahead and show that, and then I think I'm about done. So we would have a, still keeping them in alphabetical order. We're going to need the address and the size. That will not return anything. It will I will use the at forward, and then I still can keep. Why don't I just take what I need? All right, so hopefully you get the idea there. I am going to add something to the agenda just to put it right out there in front of you so that you So this heads up from the last lab that you did. Those min-max comparisons will not work if you don't typecast. HLA will not know that it's supposed to be interpreting signed values unless you tell it to do that. So my examples last week did that, but a lot of you probably, I guess, didn't either look at my examples and also didn't watch the lecture video. But so I'm probably, telling people who already know this. But anyway, if it helps get the word out, those min and max algorithms won't work unless you typecast in 16. They won't. How do you know that? Because you should test your own code with negative and positive values. That's what I do, which is how I uncovered the bug for so many people who hadn't done that, which means I was the only one that tested their code for them. So min and max, those won't work unless you do typecasting. The other thing to think about is the other places where you must typecast. And then I will leave you with this idea. If in doubt, typecast. Oh, sorry, Asnam. I'll go back. So there's I missed the question in chat about what does the @returns do. So as I was saying before, @returns doesn't actually cause a return value like we're accustomed to. What it does, and notice that the EAX is in quotes. What it does @returns is it allows me to call the function as part of other calls. So I'll go back and remind you, this is what I talked about first. So the old way of doing it before we had @returns is we'd have to call create array. We would have to remember that the create array is going to leave an address in EAX, and then we would move that EAX to our long-term storage. That's the way that we've been doing it all semester. But if we have @returns on the function, we now have the option. We don't have the requirement. It'll compile either way. But we now have the option to eliminate the extra instruction. So instead of create array and then move EAX to MArray, I can just say move create array, which calls the function, and because that @returns places the EAX right there, copy that into MArray. So you can use either style, up to you. I kind of like the compact style, and also I wanted to leave it there so that that would sort of tie that off. Okay, good. I answered that question. So anyway, that's my last thing to remind you about, is that if you are in doubt and you are accessing your dynamic array, if in doubt, typecast. The way to erase doubt is to test. So if you run the program, give it a mix of values, negative and positive values. You should also, by the way, some ideas about testing your min-max algorithms. You should do a setup where your minimum or maximum value is the first value, where your minimum maximum is the last value, where the min-max value is duplicated, so it appears twice in the array to make sure it doesn't bust your algorithm. And your min-max value somewhere in the middle. So this is like your chance to really like bring one home as a perfect piece of software. It's very small. It doesn't have that much stuff going on in it. It's going to be a huge, nasty HLA coding mess, of course, but it's not really doing that much. So this is a chance to bring together all the skills that you have. You know what are the best ways to test your software, to test your algorithms. Those are just ideas about testing minimum and maximum. Testing sum and average, it should work against all zeros, as an example. It should work against a sum that adds up to 0. It should also work if the sum is negative or if the sum is positive. So a variety of things to think about. I do have one more that I will add. So the div for average, sign extension is going to be required. And in this case, you're going to need a word to double. I'll have to look. I don't remember off the top of my head what it is. So that's the setup. And then we need sign extension. And is it, it's a not, it's a word to double. What does that look like? I forget off the top of my head. What lab was that? Let's go look. Let's go hunt it down together real quick. That'll be the last thing I do. It's 1:37. So let's go hunt down together what the sign extension will be for doing the average in this project. So if I go back to the home page, I'm going to look for Tues complement. And maybe I didn't have you do sign division, but I feel like I did. Signed representations. I never did a div, did I? So we need to get that. Signed and unsigned numbers. We'll just use the book and we'll hunt it down. Sign extension. The one that we need is for 16 to 32 bits. Here it is. Convert word to double. So we'll need to make sure that we bring this up. In fact, maybe I should add it to the sample just so you can see that. Word to double. Yeah, I better leave you with that before I leave you. So I don't think we've done a signed extension, so now we get to do one. So when we are computing the average, the way I would do it, I am alphabetizing all of my forward declarations and definitions. So we're going to have the average of, give me an address, give me a size. I will return to you a 16-bit value because the average of a bunch of int 16 should be an int 16. Forward, and then I will, in fact, I'll just give you this one for free. Partially. Take what I need. To do still. Yes. Okay. So Evan asked in chat, we're going to get rid of our high-level decisions and our high-level loops and write those in pure assembly in the next 2 weeks. So can you turn in your second project using everything low level? And you most definitely can. It's not required, but I encourage it. It's good practice. So yes, you definitely can, if you like, convert some or all of your decisions in your project to the assembly style. And you also are allowed to convert some or all of your loops to assembly style so that you get the extra practice. You definitely can do that. Good question. Okay, so I'm going to leave you with some breadcrumbs for computing the average. So assuming that our sum returns a value, so we can do a so we call the sum. That's going to be in AX. So then we are going to sign extend. And the catch here, and maybe I'll get a chance to talk about it again before we're totally done. But this convert word to double, what it does is it looks at the value in AX, and if the sign bit is a 1, it actually copies all 1s into DX. The effect of copying all 1s into DX for a negative number is that effectively DX colon AX for the division is the same negative value that it was when it was in AX. If you sign extend AX and there's a 0 in the sign bit, it will copy all 0s into DX, which means that it maintains its positive value when you combine DX and AX together. So it's weird. Division is very weird in x86. So what we used to do for unsigned is we would simply move 0 to DX. But the problem with moving 0 to DX is that we ruin negative values that way. So there's actually an x86 instruction that will do the work for you of copying all 0s or all 1s based on what is needed, so that when the division fires up, you have the correct value across that 32-bit combination. Then we will div. Oh, the size is going to be awkward for this one, isn't it? It is going to be awkward. I think I'll just use B. And then I will just use the lower end of B, but that's fine because the biggest value that the size will ever be is 10, which means that all of the important data is in BX anyway. BX, AX. All right, so there's the compute the average algorithm with this special new thing that I will mark with stars. So it's the one that's the major kind of weird thing we are doing in the project that we haven't done before is how do you do division on signed integers? In fact, I did it wrong. It's idiv. It's slightly different. That's the one place where that matters. So anyway, the whole algorithm is there. Hopefully it just works for you out of the box. And if you want to go read up on what CWD does, you can just Google x86 CWD and you will find many descriptions of what that is. It's also in our book. That will be my closing thought. So I went and looked for extension in the book, but if I had done CWD, I also would have found it. And it's in this section. I just did a find on the book. But anyway, it's in a section called Sign Extension, Zero Extension, Contraction, so that you can read more about that issue if you want. Otherwise, I'll try to remember and I'll try to bring it back up in the next couple of weeks so we can do a couple of examples on it. Maybe someone in chat will call me on that and help me remember to do some signed division so that you've seen a few examples before you have to employ it on the project. But I will try to remember. Okay, it's one of those weird ones though. So notice converts the word AX to a double word in DXAX. How the heck does it do that? It just does. It's one of those hardwired into it things. So CWD basically promotes AX into a 32-bit value that lives across DX and AX joined together. It's just a weird thing. Okay, so you can read more about that. I will try to remember to do some examples of it, but I don't want to, I said I was going to try to get done a little bit more efficiently today since this is meant to be a holiday week. So I will post this code at the bottom of the lecture page so that you have kind of my idea about getting set up. And same goes, by the way, for @forward and @returns. You can hunt those down in the HLA book. there's a link to it in this week's reading. So if you want to kind of get more of the gory details of it, you're certainly welcome to do that. And if you have questions about those things, in the next 2 weeks, we should have plenty of time to address those as we build up toward doing the second project. Okay, I'm going to call that done so that this doesn't become not shorter than normal. Okay, so no assignments this week, no discussion, no homework, no lab. Hopefully there's something in here to at least get your juices flowing a little bit. There is the algorithm for, at least partially, for how do you compute the average in this project. So I will post this code to the lecture page for this week, and then that's it. I'll see you on Tuesday next week. Thank you, Evan. Everybody have a nice Thanksgiving. Appreciate it, Druid. You guys take care. I'm not doing office hours on Thursday, so you'll see that all my appointment blocks are canceled. I didn't figure anyone was going to come anyway, but just so you know. Okay. Have a great week. If you get some downtime, hopefully you do, then enjoy that, or whatever it is that you're making. Hopefully you can make some good use of the time to relax, catch up on school, get extra hours at work, whatever it is. Anyway, see you on Tuesday next week.